Okay. The experiment for the photoelectric effect. Yeah, again, the book I was using earlier from Gill Books, which has a lot of these experiments outlined, leaving cert experiments. So it's really nice. It's really nice. Here is solution here using the gold leaf, which is the one I always think of from the books, but there are others. So for the experiment, well, let's just look through it here. So you've got your UV source. You've got a zinc plate, and the procedure is to charge the electroscope negatively, then to shine the UV light on the plate. So first you charge this, you give this a negative charge firstly, then you shine UV on the plate. And the leaves, this leaves on the gold leaf electroscope. Oh, this is so small. I'll just zoom in. Let's make our lives easier. Yep. Okay. So as I was saying, what you need is the electroscope, and you first start off by giving it a negative charge. And you've got your UV light source and your zinc plate on the top. So the procedure is, after you charge it, is to shine the UV light on the plate. So what's going to happen is when the UV light shines on the plate, it's going to free electrons. That's what's going to happen. That's the photoelectric effect, that the photon gives the trapped electron enough energy to be freed from the surface. And these leaves collapse. So the negative charge is being lost. The electrons are leaving the plate because they're freed. They're given energy by the UV light. The reason the gold leaf here is deflected is because like charges repel. So the negative charge here and here pushes them apart. But if it loses its negative charge, then this will collapse. And the only way it can lose this negative charge is if the electrons leave the zinc plate, and they leave the zinc plate because they gain energy to leave from the photons striking it from the UV light. And that's the photoelectric effect, and that's the experiment to demonstrate it. Okay, so that's the experiment, and that's a 9 marker, and yeah, this is more than 9 marks, so maybe in the marking scheme when it's released they might go with 333. I would make it 9 marks. It could be okay. Okay, now on to the calculations. Light of wavelength 450 nanometers is shone onto a metal that has a work function of 2.4. Calculate the maximum speed of the electrons emitted. So that's the formula. HF equals the work function in joules plus the kinetic energy. So really we're looking for the kinetic energy here. So the kinetic energy will equal HF minus the work function, but kinetic energy, that's a half mv squared, equals HF minus the work function. So you get V, that will equal HF minus the work function over a half m, or you can put the 2 on top if you like, square root. Now, I have to take the calculator out. So let's see, root h, do I remember? Yeah, I got h. And the frequency, now they gave the wavelength. So now we have to use the formula, wavelength is c over f, so we're not quite there yet. So it's going to be hf minus 2.4 times E to convert it into joules. Oh, and the F, of course, is C over the lambda is C over F, and the F is C over lambda, so it's hc over lambda minus the work function, which is going to be 2.4 times E, all over half the mass of the electron. Okay, now I can type it in. If I can. Okay, minus. Okay, and then I have to divide this by the wavelength, 450 nano, that's 10 to the minus 9. Okay, and then half the mass of an electron. Right, so I've got hc over lambda minus 2.4 times electron volt constant, which is just the E constant, over half the mass of an electron. So I should get a pretty big number. Yeah. So if I want to go with 3 significant figures, 353,000 meters per second. That is the speed of the electrons that are freed when light of wavelength 450 is shone onto a metal of work function 2.4 electron volts. It's actually quite a complicated calculation. It's observed that as the wavelength of the incident light increases, the speed of the emitted electrons decreases, and eventually no electrons are emitted. Explain why. So what's happening, as the wavelength increases, the frequency decreases. As the frequency here decreases, in the formula you can see quite clearly that the V decreases. In fact, roughly speaking, looks like the relationship is V squared is proportional to F. But what will happen is as the F decreases, eventually HF will equal the work function, and so you'll get a 0 here in the numerator, and then the V will be 0. That's sort of the mathematical explanation why. But what's happening physically, if you want a physics explanation, is that as the wavelength increases, the frequency of the light decreases, and that means the energy of the light photon decreases, since the energy of a light photon is proportional to its frequency. So I'll say that again. As the wavelength increases of the photon, its frequency decreases. Therefore, its energy decreases, since energy is proportional to frequency. Therefore, less energy is given to the electron. Therefore, after the electron uses up the energy to free itself, it has less left as kinetic energy. And if you give it too little energy, eventually it won't even have enough energy to free itself. So that's the explanation for the observations. Sorry I didn't write that down, but hopefully you're able to follow what I'm saying here. 19 marks, not surprising. I guess this second part here would be pretty big. I'm not sure what the split would be exactly, but I really hope that you get most of the 19 marks for the calculation. Could it even be 15-4? Would that be too much? Don't know. I'll have to look at other exam questions to get an idea. Okay, so I've done the experiment. I calculated the speed, and I explained the observation. Okay.